Não sei se você estava aqui ontem. Não? O primeiro dia tu estava? Tá bom. Não perdeu muito. Ontem a gente fez a gente começou a parte 2 desse mini curso com uma introdução com o Python. Não sei se tu conhece o Python. Tu conhece já bem? Tu já faz coisas? Então os dois primeiros secções era sobre uma apresentação de Python e do package que a gente vai usar. Será que algumas pessoas têm dúvidas sobre ontem, a aula de ontem? Vocês pensaram de noite sobre... Achou uma pergunta para fazer, não? Hoje? Quem tem um computador hoje? Computador? 1, 2, 3, 4, 5, 6, 7. Então acho que dá para dividir um por um. Bom, 2 pessoas só com o computador. Então, se vocês querem se arrumar para estar 2 pessoas, pelo menos com um computador, seria legal. E também tem tomadas aqui. E eu acho que ainda tem umas tomadas lá. E as pessoas que também estão ao vivo, eles podem fazer o exercício que a gente vai fazer juntos, ao mesmo tempo, ao vivo. Bem? Vocês vão conseguir seguir com uma pessoa? Se vocês querem mudar de vaga para... É procurado mesmo. Ótimo. Então essa parte this part with the PyMO tutorial is divided into, we first look at simple example which are linear, okay? So the first family of classes of problem we saw yesterday and the day before. And the second subsection, we will see one example, maybe 2, of nonlinear problem. Really general nonlinear problem. And tomorrow we will be having a small lecture about microgrids, and at the end of this lecture we will apply the tools we've seen today to the microgrid and the energy management of the microgrid. Okay? So let's start first with some simple examples so you can use and start to learn how to use Python to make optimizations. So the objective of this example, as I said, it's a really simple example. It could help you to understand how to use Python and PyMO, so create variables, solve optimization problem, define variables, define constraints, define objectives, set and parameters, etc. And we will be using Python as well to make some basic scripts, workflow, and programming data analysis. Everything okay? You are connected? You have Wi-Fi? Não vai ter? Okay, so we have one problem here with Wi-Fi. Otherwise, it's okay. Okay. So there is the knapsack problem, which is a problem I told you the first day. You know, the thief problem. O problema do ladrão. You remember that? Remember that? So the knapsack problem is we have a given set of goods. So we have to select some items. Here in the example, it's a hammer, a wrench, screwdriver, a towel. A wrench in Portuguese, I guess it's inglês, chave inglês. É isso, né? Chave inglesa. So you can choose some items, but every one of them have a given weight. Okay? Here. And every one of them have a given benefits. Okay? So they all have a weight and a benefit. And sometimes you can see there is a good benefit and a small weight, which is a good object. And sometimes you have a weight which is really high, and sometimes the benefit is not that good. Okay? So it's exactly the thief problem as well, as I explained you yesterday, or 2 days after. And the goal of this problem is to maximize the benefit or the use or the value of the object you're going to pick, but you're limited to some weight. Okay? It can be a volume, because my example was with a volume. It can be a weight as well. Okay. Does someone knows just right now, the solution of the problem? Can you deduce from this table, which is a really simple example, the optimal solution? Yeah, it's not that easy actually. Even for a small amount of items, here we have 4 items, it's not really easy to find the optimal solution. And even if we find a solution that seems to be the best, we have no clue if this is the optimal solution or not. Okay? So that's, in these cases, we are going to use optimal and optimization. So here, I just noted some symbols here. So A, it's the set of items available. Okay. B is the benefit of each item. W is the weight of each item. And big W max is the maximal weight of the sum of all goods you're going to buy or take. And X is the discrete variable, so if I select it or not. Okay? So here in this example, based on what we saw yesterday and the day before, what is the class of the problem? What is the class of the problem? You wasn't there before. Yeah, yesterday you weren't there.
Sorry about that.
Yeah, it's an integer programming, right? Because we have only one vector variable, which is x. X is an integer. It's or 0 or 1. And we have one constraint that is linear, which is the sum of all the weights. and one objective, which is the sum of all the benefits. Okay, so the objective is linear, the constants are linear, and we have the variables defined on a discrete set. So it's an IP, okay? So we know for sure that we will have a solution. We have one, maybe, or a lot of solution. Maybe it's not bounded, maybe it's not feasible, but at the end of this exercise, we'll be sure if there is one, many, or no solution. But that's kind of good to know that in some basics of mathematics, because we now know how to handle it. Okay, we know have some results about it. So here I wrote down the equation. So we want to maximize the benefits. So the benefits of all the goods. So if I take, for instance, the first, I will sum up the benefits 1, and if I don't take it, then the product is 0. And the constraint on the maximal weight is here. Okay? So the sum of all the weights of all goods must be smaller than W max. Okay? That's easy, right? It's really easy. One objective, one constraint, and a variable defined between 0 and 1. Or 0 or 1. Okay, so we defined the variables, the objective, the constants, the set, and the parameters. Here, everything should be really clear for you, okay? Here in Python, this is the example. Okay? So that's what we are going to code now with our laptop. So if you want to connect if you didn't do it yesterday, we have to go to GitHub. Here we find my name. In the users, I'm the only one with this name. And this is the gallery I made for this course. So maybe if you put this name in Google, maybe we'll find it as well. I'm not sure. Or maybe you can directly take this address, which is github.com, right? My name, a V, and the name of the gallery. You got it, right? You are in the... Just checking if everybody is good. You good? You want... Oh yeah, you did it. Okay. And over there here, too? You did it too? Ok. Conseguiu? Tá sem internet? E os outros? Ah, legal. Tem uma rede aqui só de vocês?
Chamada certo, tem que isso aí. Aí a senha é BBA, repete 3 vezes. BBA, BBA, BBA.
Assim? 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 Assim. Uma vez, when you are in this page, you can click on the binder launch button, and you. This is GitHub. You go to GitHub. Eu vou fazer de novo. Agora acho que você é muito lento. Muito lento. É isso. You go to GitHub. And you can look for my name, which is this one. Me chamaram? Ah. Deu? Deu certo?
É, tá devagar.
É.
Vou tentar.
E depois tu pode clicar nesse botão, quando tu chegar no coisa. Então eu vou continuar para as pessoas que já são conectadas, tá? So you came up with this page, which is a Jupyter Lab page. Here you have some folders. So here in this folder, for instance, you will find my presentation. If you click on it, you will be able to download it or to follow the course at your speed. Okay? If you want to go slowly or more quickly, you can do it as well. It's okay for me. If you go back here, you will have some tutorial. So there is some Python tutorial that I didn't do yesterday. But if you want to do some exercises, I recommend you to go there here to use that. This is the Pyomo tutorial. So there is another examples here. I guess we will be doing one example from here. And I have also other exercises that we are going to start right now in this folder. You have normally access to exercise without solution today. And after today, I will give you the solutions, okay? So no worries if you don't finish all the exercises or if you don't save it, there are no problems. You will have the explanation and the solutions. I had a question last time about what I was using as a package, Python package. So here I have my environment. Okay, so I'm using these dependencies. So all of those are packages that you could install on your Python distribution if you want to install it on your laptop. So Pyomo is the package that we are using for the modeling, okay? But there are others. So NetworkX is a package which is interesting for network optimization, okay? This is a graph analysis package. Panda, which I already told about, it's for data analysis in time series. NumPy, which is a general package for vectors and matrices analysis. And here it's the funny part. The three packages here are actually solvers. They are wrappers that are linked to solvers, okay? So those are the Python package to use glpkey, which is an open source linear solver. CoinCBC, which is another linear solver for integers and linear programs. And IPOpt, which is one of the best non-linear solver. Okay, So if your problems are nonlinear or convex, you can use IPOpt. We will be using IPOpt in the following, in the part where we try to tackle some nonlinear problems. Matplotlib is just plots, so figures with Python, really similar to MATLAB. And Pyomo.solver, it's a, let's say, it's a dependence of Pyomo, so no problems. There is no. So for the beginning, we can go into exercise without solutions. Exercises. And we are in the Pyomo fundamentals at the beginning. So the following of my talk will be about this exercise 1. Okay? Snapshot problem. So if you go back there, so with your computers, you stay with Python, okay? Step by step, you will be able to write down the codes, and I will try to explain it at the beginning, okay? So we will start with this simple example, and I will try to explain you which is what is what, okay? You had access to it? Não chegou. É isso mesmo.
Tem uma outra rede de internet que é melhor, mas eu não tenho acesso, porque eu não sou aluno daqui, que é essa daqui.
Você não consegue...
Não, essa aqui não, porque é pra quem é aluno. Esse login e senha. Aí, e a rede que eu consegui não tá tão boa.
Este não é de roam também. Tu não tem acesso a de roam?
E a rede boa é essa aqui, vai ser sem fios. Aí é só pra quem é aluno da instituição.
Entendi. E será que tem alunos que podem te dar a senha?
Eu mandei mensagem pra um aqui, tô esperando. Mas
Tá bom.
não sei se eu vou conseguir.
As outras pessoas foram procurar um computador? As outras pessoas foram procurar...
Eles foram uma apresentação de 5 minutos que eles têm que fazer e já voltam.
Ah, tá. 5 minutos de apresentação de quê?
É porque tem um professor da manhã que é relacionado à pesquisa deles.
Sim.
Aí eles vão só expor o que é que eles estão trabalhando e já voltam.
Tá bom. Não, tu vai no Pyomo Fundamentals. Isso. Exercício 1. E é o Snapchat. É isso. E se você quer dar o play, tu pode fazer run. Tem que ser. Ou tu pode fazer control. Control. Ah, não. Ele faz plus new console Python 3. Tu vai ter uma console. Aí tu pode botar embaixo. Tu pega esse, tu vai botar embaixo. Isso. E aqui nessa consola tu consegue escrever. Tu consegue escrever run this. Eu já vou te mostrar. Tá bom? Vamos lá. Então, mais ou menos, todo mundo chegaram a se conectar. Aqui tá bom também? Tá certo?
Certo.
Tu conseguiu entrar aqui, ok. Levanta a cabeça um pouquinho. I will now do some description. So here the code starts with the loading, importing the function of Pyomo. Okay? So Pyomo can understand everything we are going to use for Pyomo. These are just the data we saw. Okay? So this is the set of the object I have. This is a dictionary, as we saw yesterday, so between brackets. The hammer have a benefit of 8, the wrench a benefit of 3, etc. And the weight of all the objects are also in the third line as a dictionary. Okay, so every key has their own value. And there is a constraint on the maximal weight, which is here is set as 14. Okay. So this line is responsible for importing all the objects of the package Pyomo into the workspace. Okay. But usually we don't write just that, but we write this so every function can be accessible directly. Because if we don't import star, import all, we will have to write every time we want to use a function this line, and it's more it's easier to write it like that. So we prefer the import all like that. To clarify the notes here, all the symbols that come from the Pyomo package will be in green. So this first line, as we saw, imports all the Python function and objects into the modeling environment. Okay. And the first line, model equal concrete model, instantiates one problem. This is the first line of the problem. Yeah, I create a model, an empty model. Okay. So model is a local variable, and concrete model is a class that is imported from the Pyomo modeling environment. If we come back here, so I created the model, and then I begin to define my variables. So the first variable I can define, and I have only one variable in my problem, is x. Okay, if I pick or not an object. This variable is indexed by the set A. Okay, because we have a lot of different objects, so I have one variable for each object. That's the way I code it in Python, in Pyomo. Yeah. So the variables. The model dot my variable is equal to a variable. So this is a class of Pyomo. And here in the brackets here, you will find some arguments. Here in this example, we define the domain of the variable, and here the domain is non-negative reals. Okay, so here I declare a variable, which belongs to the model, and is a variable within the non-negative reals. So positive plus 0. Okay. There is also other possible arguments. We can put arguments like bounds. We can initialize variables, or both. Okay, initialize and define some bounds. Non-negative reals, it's exactly the same than defining bounds like that. Okay, 0 known, it's like 0 and infinity. Okay, so it means there is no upper bound. Okay, when we define objectives, so it's the same syntax, the model that a variable, which here I call objective, is equal to objective. So this is a terms of Pyomo, it's a term of Pyomo. And between the brackets, I have the expression of my objective. Okay? And in the expression of my objective, I will find the variables model.y, model.x, and an expression. Like here it's a quadratic expression. More than that. I can also define the sense of my optimization. Okay? I said in the beginning I was working only with minimization objectives, but here in Pyomo you can work with minimization and maximization. This is the same. Okay? Usually when you don't put the sense, Pyomo assumes that it's a minimization problem, which is more common. The constraints, now we can see the constraints. They are defined as the same. So the model dot a name of a variable equal this Pyomo object called constraints, and inside the constraints I have an expression. Here it's another expression. It's not just an expression, it's inequality. Okay, so there is an expression here, a sign, and another expression. Okay. For instance, b plus 5c in this example smaller than a. Here we assume that b, c, and a are variables, right? But they may be parameters as well. Another example here of a constraint is defining an expression as a tuple. What is a tuple? Tuple, it's brackets, objects, and commas like that. So here, basically, what it does, it's at the same time two constraints. This expression must be smaller to 1, and there is no lower bound. So basically, it's the same than that. Okay, here. So 3 tuple specifies lower bound expression, upper bound, and 2 tuples specify an equality constraint. All the components as we saw, expression, constraints, variables, parameters, can be indexed. So the indexed is the objects I have in my problem, okay? So here when I write this, model.x equal var brackets a, and a assuming it's an index, it means that this line will create actually 3 variables indexed by 1, 2, and 5. So in my example where I had the wrench and the hammer, I can index my variable with variable indexes as well. We won't be using that in this problem, but in the next one. Okay, this is quite important as well. Let's say that I define a first index, e.g. x for index, is a range from 0 to 10. Actually, 10 is not included. Okay, it's 0, 9 here in this example. I define one variable which is not indexed, so it's only one variable a. I can define here another variable b which is indexed with this. So here actually I will have 10 variables. Okay, b1, b2, b0, b1, b2, b9. Okay. And my constraints here is an expression, and here I can make a sum of all the b variables, and I make a sum over the index here, idx. So Python actually understands list comprehensions. It can sum up this, okay, which is not, I guess in Python, in MATLAB is not really that simple. We have to make a loop and add to a variable, to create a variable for that. So this is simpler here. So at the end, if we remember now our example, I have the import of Pyomo, the definitions of the data I will be using, and here begins the creation of the model. I create the model, which for now is empty, okay? And step by step, I will define my model. I create one variable, which here is indexed by A, and it's defined over binary domain. So it's or 0 or 1. Okay? So with this line, I created 4 variables defined in 0, 1. Here I create my objective, define my objective, which is an objective, the expression, which is the sum of all the benefits of all my variables for any I in A, which is the index of the goods I will be buying. And this is a maximization problem. I want to maximize the benefits of my problem. But I have a constraint. My constraint can be defined here. I have a model.weight, which is a constraint. And here is the expression of my constraints. The expression is the sum of all the weights of all the objective that I pick up, that I selected, for any I into the index A. And this sum must be smaller than the maximum weight. Here I ask for a solver. So I create a solver, which usually is called opt in the examples. And I'm calling the solver factory. Solver factory is once again a Pyomo word. And I'm calling the solver GLP key. And GLP key, I've told you about that already. It's a solver which is quite used and for linear programming and integer programming. And as we know that our problem is integer, we can select this one. Okay? And then I can just have the results, saying results equal opt.solve the model. And here this argument is just saying I want some verbosity. I want all the results, all of the message of the solver. It's just an option. Okay, this one is optional. And here I can print the model. So let's go to the actual problem so we can try to execute it. I will close this so I have more space. Okay, so in the new console, it can be a console, it can be your terminal here if you have installed Python. I just asked for him to run the snapshot problem, so this file. It's really similar than MATLAB actually, right? The console in the, okay. And here are the results because I asked for him to display the model. Conseguiu?
Foi que o povo deve rodar.
Ah,
Aí tu tentou.
como é que é? Tem que ser no meio mesmo?
Então o módulo tem que importar.
Fazemos, tá esquisito isso. Oi? Sim. É 0 ou 1?
Existem outras possibilidades, outros formas.
Claro.
Tu fiz isso, né? Ixi. Não entendo isso. Conseguiu fazer?
Professor? Professor?
Não tá. Tá funcionando? Tá funcionando não aqui? Não, aqui não funciona. Tá funcionando não?
Não consegui ver.
É, porque ele está falando essa coisa. Não, mas...
Assim?
É isso mesmo.
Não acho.
É nada, saque. Tu tá onde? LS? Escreve LS. Tu não tá no... Vai no exercício, Wizard Solution.
Por quê?
É, mas o console precisa ser dentro da mesma CD. Exercício. Sim. Depois vai dentro do exercício. Vai em movimentos. Tu tem que ir até onde é. Opa! Mas não entendo porque funciona comigo e não... Tá bom. Acho que não deveria funcionar, então não funciona ainda. Não está funcionando aí também?
No modo play caiu.
Ainda não? Está funcionando só com o de lá, né? Está funcionando aqui no teu computador. E aqui, talvez tive um problema com aquele... Provavelmente a gente vai ter que importar, só que talvez no intervalo a gente faz rapidinho, tá? Então a gente pode seguir juntos no meu computador. Vai ser mais fácil para todo mundo, tá? Então aqui o resultado. The results here are the variable x, which is the size of x is 4, because we have 4 objects that we can pick or not pick. And here are the optimal values. So 1 means that I took it, okay? And 0 means that I didn't took it. Which is quite strange. Sim. Vamos ver. So the solver said that the status is okay, termination conditions are optimal, and branch and bound. So this is the algorithm that's really used by GLPT. Defined one subproblem. Okay, it resolved the problem in 1 milliseconds, 10 milliseconds. And the solution must be this. This is quite weird. Let me check on the presentation. So that's the results that we have when we put all together and we do that. Python snapshot.py. This is the results. So there is a 0 for the branch, and we have this expression, which is okay. And the objective, the value of the objective is not shown here. Here, the value of the objective, if I ask for a display to display the model, the value of the objective is 25. So that should be the output you should have. I don't know why it's not working on your computers. Maybe we take some minutes to find why there is a problem on the computers. In the meantime, I guess you can take a coffee, and I will take a coffee myself, and we try to fix the problem for the 2 or 3 computers which have the problem. Is it okay? Como?
Não poderia repetir os elementos. Por exemplo, 3 toalhas e um martelo.
Ah, não.
Dá no número binário.
Yeah. Binária quer dizer 0 ou 1.
Mas eu poderia trabalhar no domínio.
Poderia. Como? A resposta é essas values aqui. So we pick up the hammer, screwdriver, and the towel. And the wrench, which has a low benefit and a high weight, we didn't take it, okay? And the final value of the objective is 25.
This is 25 is the benefits.
Yes, this is the benefits. This is the objective, which we call value. In our problem, we call the objective, we call it value. And so here the value is 25. This is the maximum. And the constraint, which was the weight, the upper was 14, but actually we reached 12. Other questions? If no, we will start the break, and I will make a tour to see what's the problems. Então isso é a solução. A gente pegou o hammer, screwdriver e o towel. And all the constraints were good, okay? Because the final value of the constraint is 12 and the upper value is 14. So, all right. This is some exercises, but as we don't have a lot of computers, we are going to pass it. But if you want to do it at home, if you want to exercise yourself, you can take the presentation and follow the course. And I give you the solutions maybe at the end of the week or something like that, okay? This is another example, and it's quite nice for us. It's a little bit more complicated. This example is called warehouse location. So those two examples are really basic and well known for mathematicians. This one actually is geographical problem. So here in the map in the US, we have some customer location. And here we have potential warehouse location. So it's potential warehouse locations. It maybe the company will create a warehouse here, here, or here. And the problem is to find where is the best location for the warehouse. Okay? This is the optimization problem. Because we want to minimize the cost of the serving consumer, finding the best location of the warehouse. The first time it was exposed, this problem, it was exposed as it is now. But in engineering, electrical engineering, we can think about other kind of problem which is the same. For instance, electrical vehicle. We imagine that there is a lot of clients with electrical vehicle. Where is the best location for the charging stations? Okay? Or where is the best location for batteries or storage system in the network? Okay? So this kind of problems is really close, and it will be exactly the same as this one. Okay? So in this problem, it's a little bit more complicated than the thief problem. We have to determine a set of P warehouses chosen from a possible set W. So here there is 3 possible sets, and we have, for instance, have to pick one of the 3, for instance. To minimize the cost of serving all the consumers. It's important in this sentence, all the consumers. It means that we should serve all the consumers and not just a part of it. Here in this following, DWC is a cost of serving the consumer C from the warehouse at location W.
Pode falar para ela o que a gente está fazendo? Fala do problema da bateria, de charging station.
So the objective function is actually the sum of the cost multiplied by x, which is the fraction of the demand of each consumer. What does it mean? If we put a warehouse here, this warehouse will be able to serve this one, but also this one, and this one, and this one. Okay? So the x is a variable, and it can be between 0 and 1. 1, it means that all this warehouse will serve only this one. Okay? So it would be xwc equal to 1. You got it? Okay. The constraints are the sum of all the x value have to be equal to 1. Why? Because again, we have to serve all the consumers. All the consumers has to be served. So this equation guarantees that all the consumers are served. Here it is the customer C can only be served from one warehouse W if the warehouse W is selected. Okay? So it's a new constraint. And here the value Y, it's a variable, and it means that at the warehouse W we actually created a warehouse. Okay? So the set of possible candidates and Y is 1 if we actually created a warehouse, and 0 if there is no warehouse on this set. Okay. So if, for instance, we have a Y from a certain warehouse equal to 0, then this X will have to be 0. It means that if there is no warehouse, there is actually no serving services from this warehouse to the consumers. Okay? So it makes sense. The consumer can only be served by a warehouse that is selected. And Y is defined in the binary domain, 0 or 1. So what's the key difference between the thief problem or the snapshot problem? Is that here we have a sum over 2 indexes, so it's a little bit complex. It's a matrix instead of a vector. Here we have a sum of continuous variables, so the optimization variables here are both binary and continuous. Whereas here we had only binary variables. Remember? So here the constraint was just one constraint. Okay, it was only one sum, and it had to be smaller than W. Here we have a sum. We have a constraint which is much more complicated because here we have actually 4 constraints. Okay. So what's the class of this problem? We have variables that are both integer and linear or continuous, and we have objective and constraints that are linear. So which family of problem is it? It's the mixed integer linear programming, MILP problem, okay? So this is the mixed integer linear programming, and we know that using a good solver like GLPKey or CoinCBC, we will be able to solve this problem without any questions. I mean, without any doubts, we will be able to solve this problem. So here the difference. The snapshot problem, all the constraints are singular. It means that there is only one constraint. They are not indexed by. And the warehouse location problem, which can be also a battery or a station or charger location, there are multiple constraints over indices. So it can be really a big problem. It means that if we have a lot of possible warehouses, a lot of possible customers, it means that the problem will grow bigger. It is possible in Python to create constraints over indexes really easily. Here, for instance, I create a function. In the argument, I have M, which is my model, and C, which is the index of the customer. So in the possible warehouse, I define a list. So here it's an example in the United States. So there is a possible warehouse in Arlington, Memphis, Ashland, and there is customers in New York City, Los Angeles, Chicago, and Houston. Okay, this is a simple example with a small amount of items. As we saw, there is 2 variables. One variable which is indexed by the warehouse, but also by the customer, because it's the quantity of services from the warehouse W to the customer C. And as we saw, it's continuous between 0 and 1. For the second variable, which is binary in this problem, it is indexed on the warehouse. So the warehouse may be constructed or not. Maybe I take 5 minutes just to explain the problem. I think it's important for the new people. It's quite simple to understand. It's a warehouse position problem. Okay, so to take an electrical engineering problem, it's like we have a lot of consumers with electrical vehicles, and we are looking for the good positions of battery charger, okay, or charging stations in the city, okay. And this is an optimization problems because we want to optimize or minimize the cost or the distance between all the consumers and the chargers, okay? And this is, we can illustrate this problem like that. So here in this example, it's warehouses, possible warehouses, but in our field, it can be possible charging stations, for instance. And here are the customers. And as we saw just before, 5 minutes before you arrived, it's the mixed integer linear programming. So it's integer because we can build actually a warehouse or a charging station or not. And it's also linear because we have to consider that a warehouse can serve both this customer or this customer. So there is a variable between 0 and 1. I go back to where I was. So in Pyomo, we can describe the constraints like with indexes. Okay, and it works like that. So the model here, the first index, the second index, and here in these cases, I have this constraint to write. So for each x from the warehouse W to the customer C, this variable has to be smaller than 0, 0 or 1. This is just a small remark. It's not used for the warehouse problem, but we also can use more complex rules for the construction of constraints. Okay, this is an example where I want to write a rule with complex logic. So I want to write these equations. Cosinus for I is even and sinus for I is odd, and I can write this type of rules here. I pass this one. So if we can go back to the warehouse location, I need some data for the example. So I'm going to comment some of the data we use for this example. Here it is the distance between the possible warehouse and all the consumers. Okay, so Arlington is really far from New York City, and Arlington is really close to Houston. Okay, it's just the data for the analysis. So here is the full problem in Python, and we are going to comment line by line, so you are able to do it on your laptop as well. So this is, as we saw before, the import of the function of Pyomo. Here, this is the creation of an empty model, empty problem. This is my data. So basically, this is just for the example. So I have the warehouse location here, the city and the consumer here. The distance between the city and the consumer, I didn't put all the list because it's quite long, but you understand it. So between Arlington and New York City, there is this distance, and so on. And P equal to, it means that I want to build 2 warehouses. Okay? I create my variables. So one is indexed by both W and C, and it's continuous between 0 and 1. And the second is Y, indexed by a W, and it takes values in the binary domain. If you want, you can use your laptop to do the same in parallel. The objective, as we saw, is to minimize the sum of all the distance between the warehouse and the consumers. So it takes this form. I sum the distance, multiply by the number of exchange I'll have between the warehouse and the consumer. And it's a double sum over W and over C. And I define it as the objective, as we saw before. Here there is a constraint. It means that all the value, all the sum of exchange between warehouse and the cities must be equal to 1. At the end, all the consumer must be served once. Okay. Here I say that here it's a constraint that it say I cannot serve a city or a consumer from a warehouse that is not built. Okay, if I don't choose to build a warehouse in this city, then my value x must be 0, and it's exactly what I do here. X smaller than y. We saw it yesterday in the if-then example, a statement. I don't know if you remember that. I ask you a lot of tricks. I show you a lot of tricks to model some statements, and one of them was the if-then statement. And the answer is where this one. This is to limit the number of warehouse I will be building. So the sum of all the warehouse I'm building has to be equal to 2. So this again was a trick we saw when I asked you to pick n values from a set of m objects. You remember? It was this answer. So all of these equations I'm writing here, actually we saw it before. Here I'm choosing an algorithm. Here it's a GLP key, and for the people that wasn't there before, GLP key is a standard open source solver for this kind of problem. So a mixed integer linear programming or linear programming. And this is a print of the results. So for the people that can do it online, it's nice. Otherwise, we will do together. I hope you can read everything here. So we are in the warehouse location problem. So this is the same code that I was discussing, but in Python, okay? So here we find the model, the data. This is exactly the same, okay? And I'm asking, and I will execute this so you can see the answers. Here are the answers. So I have for my y, you remember it was if I constructed a warehouse or not. Okay? So here I decided to construct a warehouse in Ashland and in Harlingen. And the algorithm said here that the Memphis city didn't worth it. Okay, so I didn't zero warehouse in Memphis City.
Have in between values or
no. So no, because or I install a warehouse or not. I cannot install smaller in this problem. And here you have the optimal exchange between warehouse and cities. For instance, Ashland and Chicago. Ashland is a warehouse and Chicago is a city, or the customer city, and all the Chicago will be served from Ashland. Okay. For instance, Arlington from Chicago is 0, and all the goods will be coming from Ashland. So here you have the optimal dispatch of the good from a warehouse to customers. Do you have any questions? here for the results? Do you think it all makes sense to you?
What are the constraints you use?
So the constraints here are that I can build a warehouse or not. All my consumers have to be served. So there's no curtail. So all the consumers are served. And if there is no warehouse, this warehouse cannot serve a good. Okay? Questions?
The variable x could be between 0 and 1.
Which one?
The x.
The x, yeah.
But then it's only 1 or 0.
In this particular case, there is no I wouldn't say that I know for sure that it's always 1 or 0, but in this context where the model is really simple, it's made normal.
Half and 1 and or not.
It could be 1 or between 1 and 0, and in this case he found that it was 1 and 0. Maybe if we had some other constraints like the warehouse has the capacity or a certain capacity, or the trucks from the warehouse to another consumer have a certain capacity, then maybe we would have some other results more. Yeah, maybe, yeah. But in this case, as the problem is really simple, usually the answer is in the corner. Okay? Remember of what I said earlier. It's really, it's a really general problem. It's not only warehouse, etc. It can be batteries in a city, or thermal storage. It can be charging station for hybrid vehicles or electric vehicles. So these kind of problems are actually more general than we think. Okay? And they are doing the optimal dispatch. We are here doing optimal dispatch, but also optimal sizing. Okay? Because if we build a store or warehouse or not, is a sizing problem or architecture problem. And solving the X variable is actually a use or a dispatch problem. Okay? So here in this problem, we see a lot of things that might be complex in the real life.
I'm sorry, I didn't have some contrast, but you have a restriction of use now. You can use for every case in your the possibility of
Yes.
the classes, different classes.
So here, this problem is mixed integer linear programming. But for instance, if we put some nonlinear constraints, let's imagine that we are not thinking about deliveries, but delivery of power, electric power. We have some nonlinear constraints on the voltage or the current. Then we won't be able to use GLPK. Okay, we won't be able to use this solver, but we can use the same model and just pick up another solver, and it may converge, because we saw that in the case of the nonlinear program, the solver may not converge. We don't have all the good properties that we have for linear program. Other questions? So this is another exercise. It is available, and the solution will be available as well. This is a new formulation of the knapsack problem, which is a thief problem we saw before. And this is the same problem. The question one was the same problem, but using another rule definition. Okay, so if you want to do that, it's available, and the solution will be available. Sometimes in PyOmo we can define constraints like that. So which make the definition of constants really small. Okay, it uses a decorator. So decorator, I guess it's only for Python. Maybe in Julia there is decorator. I'm not sure about the other languages. It makes the code really smaller. Okay. This is an example, and this is a general notation. The object, which is our model, the component, which is a name constraint here, and here the argument as we saw before. Another thing that we didn't look into was the parameters. In model there is variables, but there is also parameters, which is value which are fixed. Okay. In PyOmo the parameters is written like that. Okay. And can be initialized using the word this argument. Okay. So here in my model, I create a new parameters with this PyOmo word, and I use 42 as an initialization. Parameters can be indexed, like with the index here, and they can be changed afterwards. For instance, I'm looking for the size of a battery, let's say. A maximal size of a battery. I can define the size of battery as a parameter and change it, and make optimization and change it and make optimization again. It's sometimes useful to have this mutable argument here. Sets, we already saw what the set is. Here we can initialize sets using this. If you do this, it won't work. It's not the same behavior. Between sets, we can do a lot of things as well. Here is a special. Yeah, here. Let's go here. We can actually combine sets, so multiply sets, make divisions, make combinations, intersection differences, and symmetric differences. And all the options are here. So you can use this slide for as a documentation if you want. Okay, if you want to build your own model. Yeah, I'll pass this one. Yeah, in Python it's interesting to know that actually it's the same for MATLAB, I guess. If you have a list, a variable, which is a list, usually it's not ordered. So if you make a loop over a vector and you want to print it, maybe the order will change from time to time, okay? But you can fix the order using this argument. Other modeling components, I'm not using that actually, but you can create a list of constraints and add constraints by constraints. So if you want to build a big matrix or system of constraints, you can use this arguments. Okay, I won't do that. So this was the in-class snapshot problem. So we should be doing this together in the course. But we did it before you came. The other half came. And that was the solution. Do you have some questions about linear programming using Pyomo?
Is there a community that contributes for solving problems and adding possibilities?
Yes, there is a big community. Maybe we can look at it. So Pyomo is collaborative code, okay, and all the code is accessible here, okay. So you can download it, install it on your computer. You can make changes, and you can also propose some changes if you want to do that. So here there is a documentation of Pyomo. Actually, it's better to go there, I guess. This is the web page of Pyomo, and here is the documentation. Here are the installation instruction, but it's already installed for most of you. And here it's the documentation. You have a book written by the people from the US. And here you have the Pyomo web page, which is the documentation for the code. So you have the installation step, of course. You have the Pyomo overview and all the Pyomo modeling components that I was explaining yesterday. Here you have some overview of Pyomo, and it explains that it includes linear programming, quadratic, nonlinear, etc., etc. There is some examples in Pyomo, so you can run those examples. The people that developed this library are not from electric engineering, so there is no example for electric engineering. In my lab, we are developing some libraries based on Pyomo to model electric engineering units. And this is also available. It's LMS2. So I'm responsible for the codes here. I can show you that I have a library. So the main idea of this library is to collaborate around models of electric engineering. So we have some installation steps, dependencies, and so on. So to get started, and the documentation of our work. We intend to build a multi-physical library. So we intend to model a lot of units, so we can build a complex model step by step. So for instance, if we go to electric, which is the main topic of our lab, we have modules for batteries, modules for main grids, turbines, and sources. In the batteries, here I have only one available batteries because it's a public. This one is a public example. But inside our lab, we have a lot of different batteries because people work on lithium batteries really detailed, other not. So here, the available for everybody is the simple batteries, and and there is a documentation about the model, which should be here, and you can access the source as well, and you will recognize some Pyomo words like here we have a variable, which is the power of charging, the power of discharging the battery, which is a variable. It's indexed by the time, etc., etc. So those are quite complex models, as you can see, because the unit of a battery is quite it can be quite complex. Okay, compared to the simple model we were looking at the beginning. But actually, this part was for tomorrow, so I will start talking about this one now. So there's a lot of collaboration. You can build models. You can build libraries of models. We can collaborate around models. If you want to work on batteries, that I don't have all the model of batteries. So if you want to develop your own model of battery, you can add it to this library, and so on and so on. There's another nice thing to know about Pyomo, that the people that is responsible for the development of this are really active, let's say. Google Group, Pyomo. I don't know if you know the forum of Google Group. There is a forum. So if you have a problem using Pyomo, here only today, or what day is today? 6? Today they didn't ask questions, but there is questions almost every day. The 5th of November, so the 2 questions here were yesterday, and there is questions every day basically, or response at least. Basically, you wait 12 hours and you will have your response if you have questions. I used to follow the questions and answer some questions as well, because I'm a part of this group. But here it's been a while that I didn't. You see, the people here is interested in modeling pipeline model. Sometimes you see, engineering problems here in this group. Let's go back to the presentation. So this is now the time. This one is quicker. Nonlinear programming are easy to write in Pyomo, but not to solve, as we saw in the first part. Okay, solve them can be quite difficult. Okay, because usually when we write equations and we know how to write them, we make some mistakes, and so what's the supported expression? So they are all really basic. Multiplication, division, exponentiation. It means the 2 stars are actually I don't know how to call this. It's not the same in MATLAB because they use the... Como se fala? Oh? Circunflexo? In-place multiplication, so it's piece by piece. In-place division and in-place exponentiation, so it's piece by piece. Here you have an example. I define a function that returns an expression. So 2 pi times r plus h. what's the surface area of an object here? Probably it's a cone, a cylinder. So I can do this multiplication. Even if m.r is a variable, I can do multiplication of variables and variables here. Okay. For the volume, it's p h r square. And here it's a definition of a constraint, because this is not an expression, it's an equation. You see that? You see the equal makes this a constraint, an equality constraints. There are all supported expression here. So the basics: cosinus, exponential, natural log, 10 base log, the sinus, square root, hyperbolic sine, etc., etc. Normally, you won't miss any really famous function. You have to import this function from the math Python package, but normally it's a basic one, so you don't have to import it or install it. Do you know the Rosenberg function? Do you know the Rosenberg function? This one. It's a highly nonlinear and non-convex problem. And it's really difficult, so it's a benchmark. Do you know benchmark? Do you know what a benchmark is? Não muito. Benchmark? Benchmark, você sabe o que é? Lá no fundo? Não muito. Benchmark é problema que não é muito físico ou muito de uma coisa muito particular, mas é um problema que não tem sentido físico, ou pode ter sentido físico, mas que a gente usa para comparar diferentes ferramentas. Por exemplo, a gente vai pegar esse problema e a gente vai usar diferentes solvers, diferentes softwares. Daí, o tempo que leva para converger, a qualidade da solução, etc., vai nos ajudar a fazer uma comparação entre solvers. Entendeu? And this one is quite difficult because he has a really large plane minimal. So there's a lot of minimal values here, but only one is actually minimal. Okay, so sometimes solver can stop there. They can stop there thinking that it's a minimal, but it's not. This is not convex here because here you have a concave part, and there's a lot of maximal as well. So it's not an easy function to solve. And here in this example, we are using IP-opt to solve this because as it's nonlinear and non-convex, we know that IP-opt is the solver for us. Okay? And as we saw on the first day, and do you want me to go back to the nonlinear problem solvers section? Maybe not. The solver will give a solution depending on the initial points. If you change the initial points, sometimes the solution at the end it is not the same. So here in this example, we initialize the point at 1.5, 1.5, which is in the middle, somewhere here. So this is really simple, but it's non-linear, so it's simple to write, but not to solve. So to write, it's easy. There is two variables initialized at 1.5, 1.5. There is one function, which is return this expression, 1 minus x squared, plus 100 times y minus x squared and all square. Rewrite the objective with the rule that we defined it above, and this is a minimization problem. So we write sense equal minimize. We pick a solver IP opt because we know that the problem is nonlinear. If we would choose another one that is not for a nonlinear problem, there will be an error. Let's do that. Here is the solution. So the two variables x and y have an optimal solution at 1 and 1. There is some numerical noise here and here. Here the objective is this one, as we said. Here we can have some more information about the solver status. The solver gives the terminal condition as optimal. So it means that at this point, he calculated the KKT conditions. You remember from the first course, or the second, the KKT condition were a necessary condition for optimality. So the solver knows that this position is optimal. We have the time, so he found the optimal solution in 30 milliseconds, which is quite fast because I have a good computer. It's simple, and it's a simple problem.
Is there a limit in the number of variables?
Yeah, of course. If the more variables, the bigger the problem, then the time will be bigger. Yeah.
Just a question of time.
The time is not just a question of number of variables, but it has an impact. Yes. Yeah. Do you have questions on the nonlinear programming part? So here there is some other exercises that you can implement if you want. And I'll be giving the solutions at the end of the course. Here I will do an example where changing the initial condition will change the solution. So if you face a problem with a nonlinear problem, sometimes it's good to change the initial conditions to be sure that your final solution is the best one. So this is the same problem. a concrete problem. I have the two same variables. I defined my problems like that, and I can solve it, okay? But now I want to change the initial point and put it at 5, okay? So I can change it like that. And I change the x, so the initial condition for x, and I'm changing from 1 to 5, okay? And every time I change it, I solve a new time, okay? And here, every iteration, I plot this optimal solution. Okay, so here I run the problems 5 times for different initial conditions: 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, and every time the solution was the good one. Okay, it means that every time for every initial points the solver reached the actual optimal. It's not always the case though, okay? So if you have other type of problems, you will need to do this. Now actually when I started the classes, I wasn't sure of the level of everybody, so it may be a little bit hard to understand here. But it's an introduction about IPOpt, which is a solver for nonlinear programs, okay? Convex nonlinear programs. So it's a little bit tough to follow, but if you are... So we recognize our problems. It's a minimization of a function, a constraint, equality constraints, and inequality constraints, and here some bounds of the variable. So the variables are defined under some bounds. Okay, the objective function is there is value in R, and the constraints are in that form. The function to be minimized is a cost or profit or measure of to fit. Okay, so this we know already. Those kind of equations are usually the physics. Okay. The Ohm equations or every physical equations you know will be seen as equalities problems, and those equations are physics, performance, or safety constraints. Okay, for instance, my voltage cannot be higher than a certain amount of volts. All my currents has to be between this and this value. Okay, so those are physical, and this is a profit. So for large-scale optimization, so if the number of values are really big, we use generally gradient-based descent solutions. It means that we already saw this equation, right? It means that when we are at a certain point, don't look at this, don't look at me. We are at a certain point, we just evaluate where we are, so the value of the function, objective function, and we evaluate the gradient. It means that the direction where the function is descending, okay? So we are just looking. Imagine if my function is decreasing this way, it means that my new step will be this way as well, okay? And step by step, I will decrease the objective function until a certain point where or the function is not decreasing anymore, or where my constraints are at a certain point, bound, okay? the constraints might be the wall, and the objective function can be descending like that, and we stop at the wall. So the Newton step, and this is the same step as in simulation. Okay, when we want to simulate, we are looking for 0, and we use this kind of algorithm as well. Okay, so it's quite the same. And this called active set strategy. Okay, and we are just looking for the KKT conditions, which are here, and we want them to be 0. Okay. So I told about this before. Actually, we don't see the other here. It's really, it's in gray, and it doesn't show up here. The IP opt uses another technique. Okay. So this is the original NLP with my constraints. And the new NLP of the IP log do this. It means that the constraints here are added to the objective of a function in the form of a sum of the Neperian logarithmic here. Okay, I passed the detail here. It might be useful if you want to use IP opt in the future to look at this. It's actually the output of the algorithm. So if you want to understand the output of the algorithm once you use it, that will be explained here. So the exit condition of the IP opt is or successful exit or successful with some problems. It may be one constraint or two that are not satisfied, or it's infeasible, or it's unbounded. And we saw this in the first day of the class, or second day. I will pass this. Yeah, this might be interesting for you if you want to use IP opt as well. There is a lot of options you can pass from Pyomo to the solver. Okay. So usually these options are well documented in the documentation website, but here I put some examples. For instance, the mu that we use is in the barrier technique can be initialized. This is quite a geeky argument, so I will pass this as well. This is the end of the Pyomo general tutorial. And this is based on 2 books and the work of 2 people. So Bethany and John here. There's a big team behind that. Actually, there's 2 main papers. So this paper is to go a little bit forward because it goes more deeply in the dynamic systems. So if you are facing dynamic systems or different order equations, there is solutions using Pyomo. And this one is for the model of dynamic system with uncertainties. Okay, so it's stochastic optimization here. Let's see. Here we already saw this, and these are for the another parts. Do you have questions for this part, for the end of this part? No? I guess we have time to begin a little bit the part 3, right? See? Okay. We can make the introduction at least. So I want you to forget all about the optimization we were just looking at, or to wake up if you were just sleeping, okay? Because it's a different part, okay? And we are now looking at real electric engineering problems and not just mathematics and codes. So in this part, I will talk about quite quickly on the introduction of the microgrids and the stakes of the microgrids integration. So why we do want to develop microgrids, okay? Why it's important to do that, why it's not important to do that, etc. And then we will go back to the modeling in Pyomo. And then I explain some the problem of energy management in the microgrid. So I will try to illustrate what's the energy management problem in the microgrid. We will do a small project using Pyomo, so we will actually solve the problem of energy management on a small microgrid. Okay. In the 5 section here, I will show, I don't know if I can have all the, yeah, better like that. In the 5th section, I will talk about electric vehicles. So why electrical vehicles can be seen as the part of the microgrid, okay? In 2017, I guess, if I remember, the world market of the electrical vehicle increases by 57%, okay? So electrical vehicles are actually booming, okay? So it's more and more loads for the distribution grid, right? So it's mainly in China, I guess, in the US, a little bit in Europe, but not a lot. I don't know about Brazil, about the electrical vehicle market in Brazil. I guess there is a market for the, como se chama? O prédio? Não é o prédio, o condomínio, né? Os grandes condomínios têm essa possibilidade ou essa nova lei de eles têm que ser elétricos, não é? Nos condomínios brasileiros grandes, assim, meio chique, tem mais e mais veículos elétricos dentro, né? Não? Eu ouvi falar que talvez no sul, not just for golf, right?
Não é realidade ainda.
Não é realidade ainda. Mas talvez daqui a pouco vai ser né? Então estou interessado também ter uns números no Brasil também. Isso é interessante. Mas no mundo geral é 57% de aumentação do mercado do veículo elétrico. Então nessa parte a gente vai falar rapidinho de como isso vai interagir com nossa rede de distribuição, como pode também ajudar a rede de distribuição. Porque, na verdade, o carro, no geral, fica 90% do tempo parada, entendeu? Tá, 90% do tempo a gente poderia usar a bateria, a gente poderia usar bateria como uma geração ou também com armazenamento, em caso de pico ou de mínimo de consumo. É isso. E se a gente tiver tempo, ou se a gente tiver vontade, a gente também poderia começar a como modelizar o veículo híbrido nessa ideia de vehicle to grid. E nosso laboratório está ainda trabalhando nesse tipo de projeto de uma forma meio, vamos dizer, meio geral, assim, no rede de transporte.
porque o veículo elétrico pode ajudar em vários tipos de nível, assim. Ele pode usar de maneira geral, local e microlocal no lado da casa mesmo. Isso que a gente pretende ver no final. Here are the main aspects of the microgrids. So the microgrids here illustrated, it's a general one. The definition is a cluster, so it's a set of interconnected sources, storage, charge, or loads, connected or isolated to the distribution grid. Okay? So here you have some examples. In the loads, you have heating for Europe, cooling for Brazil. You have transports. For renewable sources, I won't teach you that, and you know it better than me. You have renewable energies, microturbines, solar energies, windmills, etc. That can be connected to other networks as well, not only electrical networks. So in France we have gas network, but we have also thermal networks. And there is a lot of works about hydrogen networks. So the network of hydrogen. And of course there is some storage that are both sources and loads. And there is a distribution grid here that can be disconnected to the main grid. Okay. So why this organization of the microgrids is interesting? It helps to integrate renewable energies. So the problems, the main questions about this is how to integrate. There is some technological and economical balances to make here. It helps for the energy quality. Energy quality, I'm talking about low voltage or balance between phases. And the organization of the microgrid like that make it as energy management unit. Okay, so we can manage the energy through the microgrids using a master computer or sort of an intelligence in the microgrid. And this master, this intelligence, us actually, can manage economical aspects, but also ecological aspects, environmental aspects, etc. Okay, we can integrate a lot of different aspects in our management of the microgrid. For instance, social aspects as well are not really studied, but it's an aspect of the microgrid. How to increase, for instance, the access of poor people to energy and a good quality of energy. It can be an aspect of the microgrid. Economical aspect, it can be maximize or minimize our bill, energy bill. If we have a storage, we can store energy when we have too much renewable energy production without needing to buy energy from the grid. The main problems of studying the microgrids are here. The first is because this is a multi-physics and not only physics actually, because I'm talking about economy, ecology, social, technical aspects. So it's a multi-physics problem. It's a large time scale environment, okay? We are talking about converters that works at the milliseconds, but also we are talking about the lifetime, and we are talking about the pollutions or life cycle assessments. So really long phenomena, okay? So this is in seconds, the scale of our problems. From the milliseconds to some years, okay? And we are not used to deal with that. There is problems for geographic scales. It can be a problem really small with one house, only one load, one panel, or a university or a hospital, or a small quarter of a city. And the last, but maybe the most important, or at least the more difficult to tackle, are the uncertainties. What's for you the uncertainties of this problem, of one or given microgrids? We have uncertainties, for instance, the most famous one, let's say, would be uncertainties about production. Okay, I know here it will be sunny tomorrow, but it's not the case anywhere in the world. In Paris, for instance, we never know, or the weather is not really stressful. It can change every day. So that we have a lot of uncertainties. And if we have uncertainties on the production, on the wind, on the sun, etc., we have uncertainties on the energy management of our main grid. We can have uncertainties on the price of energy. Here I don't know if there is a dynamic price of the energy. For certain markets, you have dynamic prices. For normal users, the price is fixed, right? Yeah. What's the case of? In the residential, it's dynamic. Okay. Not everyone, but some of them. It's for companies or residential. Okay. That's quite new, actually. Okay. Okay. There are in France. It's actually for the moment constant, but they are thinking about indirect demand response. I don't know if you know about demand response. Demand response is the idea of, yeah, I am responsible for the network, and I have too much consumers, so I just slightly increase the price. So maybe consumer will stop using the energy. So it's called indirect control. Okay, indirect demand side management. And in the solar farm, there is some big farms in Europe, in Spain, in France, etc. There is some small companies that they have a lot of panels, and they have to fix, and they have to tell the network organizer what will be the profile of their energy profile tomorrow. Okay, and they will know only the price of energy a day before. Okay, so they have a lot of uncertainties because they don't know the price of energy only for a horizon of 24 hours. So they don't know after. They don't know in a week what will be the price of energy. So it's just to tell you that we have uncertainties, dynamic uncertainties. But we have also other kind of uncertainties on the models, actually. Our models are not real, okay? So, for instance, the life cycle of the battery, capacity of the battery, it's said to be fixed, but actually when you look at the measurements in the battery will change with the temperature, will change the humidity, with the time, the aging, and so on and so on. And it's just to talk about the battery, okay? We have a lot of instances about the battery. It's the same for old unit here. I guess it's a good introduction, and it will let you really interested to come tomorrow. Do you have other questions? Do you have questions? So this was the big introduction, and tomorrow we'll be going more into detail. I know that some professor already presented you the converter, but also all the renewable sources, right? You had all the other courses about that? What? Yes or no? I'm not sure. Oh, before?
Before, yes, you have the different power electronic aspects.
Or electronics?
Yeah, you have the problem of the grid and the more and intelligent
Intelligence.
communication for getting data and applying the program artificial intelligence. And we have a new, and there are some topologies related to idea of penetration. We have had power electronics point of view in connection with
Yeah.
the microgrid. Have a system view in terms of collecting data to see what happened, program where to put things, and so
Okay.
that was the guy from Portugal. And the other one was more information theory.
Okay. So I won't go into detail in the power electronics because you have already seen it, but it's not. I won't be in this detail. We will stay in the level of power. Okay. Dispatch power in the grid. Okay. And I guess it's nice connection between what you saw before and what we will be seeing tomorrow. Okay.
The course of Mali don't know
Yeah,
is touching the
V2G. Yeah.
I don't know if it's work dealing with that.
I will ask him. I will ask him if we will talking about that. Okay, thanks. See you tomorrow.